You've been lied to your entire life. Space is empty, right? Just a vast nothingness filled with stars and galaxies floating in the void. A blank canvas on which the cosmos paints its story. But what if I told you that space itself isn't what you think? Let's conduct a little experiment. Imagine the emptiest region of space you can, a perfect vacuum far from any planets, stars, or matter. No atoms, no radiation, nothing. As empty gets. Now let me ask you a question that will make physicists cringe. What's in that vacuum? If you said nothing, you failed the test. Because the correct answer, the answer quantum mechanics insist upon, is that empty space is filled with something. In fact, the very idea of pure emptiness, of nothingness, is a fantasy. It doesn't exist. It can't exist. And the reasons why tie into the deepest principles of modern physics. But this is where it gets strange. That something permeating the vacuum isn't matter or energy in any traditional sense. You can't scoop it up in your hands or extract it in a lab. No, according to quantum field theory, the universe's most precise description of reality, what actually fills empty space, is an entity more akin to a field of restless, fluctuating energy. An invisible, intangible substance that refuses to sit still. Physicists call it the quantum vacuum. Now, I know what you're thinking. Quantum vacuum sounds like the ultimate oxymoron. Vacuums are supposed to be empty by definition. And yet on the subatomic level, there's a sense in which space itself is eternally abuzz with activity, alive with waves of quantum possibilities. Let me put it this way. The classical vacuum of Newton and Einstein is like a still lake on a windless day. Serene, placid, predictable. The quantum vacuum is that same lake at a microscopic scale, where the water's surface is constantly rippling and churning with tiny, seemingly random fluctuations, bubbling with an intrinsic energy that never quite goes to zero. And those fluctuations aren't just mathematical artifacts or glitches in our equations. They're real. They have observable consequences. Take the famous Casimir effect, where two uncharged metal plates will attract each other in a vacuum. Why? Because the frenzied fluctuations of the quantum fields get suppressed between the plates, but keep pushing from the outside. The vacuum literally pushes the plates together. But here's where the real trouble starts. The energy of these quantum fluctuations, when you add them all up, is enormous. Absurdly enormous. If you trust the equations that say at face value, the vacuum energy in a single cubic meter of space should be around 1 times 10 to the power of 94 kilograms. That's roughly the mass energy of the entire visible universe, stuffed into your living room. Clearly, something is terribly wrong here. Astronomers look at the cosmos and see no signs of such gargantuan energy densities warping the fabric of space-time. This is what physicists dramatically call the vacuum catastrophe, and it's one of the biggest unsolved mysteries in science. Some speculate that we may need a unified theory of quantum gravity to resolve it. But here's the main lesson I want you to absorb. Space is not a sterile stage, but a dynamic entity. The quantum vacuum isn't inert. It's brimming with energy and potentiality. Virtual particles flicker in and out of existence like phantoms, their fleeting reality permitted by Heisenberg's uncertainty principle. Fields interact, fluctuate, dance. Now step back and absorb the bigger picture. Every property we ascribe to empty space, its smoothness, its isotropy, its very existence, emerges from the intricately choreographed motions of this quantum underworld. In loop quantum gravity, even the space-time continuum itself might be woven from the quantum entanglement of microscopic loops and knots. Do you see what's happening here? We're peeling back the facade of classical reality to expose the buzzing quantum circuitry beneath. We're realizing that concepts like space, time, and vacuum aren't fundamental. They're emergent. They're what our minds perceive when we don't look too closely. But as we dig deeper and deeper, we find that nature is rebuilt from the quantum up. If this has shaken your faith in the solidity of space itself, then the lesson is landed. We'll explore this rabbit hole further in the next part. But for now, I'll leave you with a closing thought. The quantum fluctuations of empty space may be imperceptible, but their effects echo across the cosmos. Just as waves can sculpt shorelines and mountains, the restless dance of the quantum vacuum may have etched the very laws of nature into existence, and we're only beginning to decipher the message. If you're ready to have your classical intuitions dismantled further, follow this series and share your reactions. The best parts are yet to come. The universe isn't just expanding, it's expanding faster and faster, like a cosmic rocket hitting the accelerator. Galaxies are flying apart at an ever-increasing rate, hinting at some mysterious force that's overpowering gravity on the grandest scales. Physicists have a name for this enigmatic entity, dark energy. But what is it? Where does it come from? That's where the quantum vacuum comes in. You see, one of the leading explanations for dark energy is that it's an intrinsic property of space itself, an energy inherent to the fabric of the cosmos. Quantum field theory predicts that the vacuum should be permeated by a uniform energy density, a kind of baseline hum of the quantum fields. And here's the key. That energy density wouldn't dilute as space expands. It would stay constant, exerting a persistent negative pressure that drives the universe to expand faster and faster. But it gets even more disturbing. The naive calculations of this vacuum energy density are catastrophically wrong. Remember the vacuum catastrophe I mentioned last time? Theoretical predictions overshoot the observed value of dark energy by a mind-boggling 120 orders of magnitude. That's like expecting a cup of coffee to boil the oceans. Clearly, we're missing something profound about how quantum fields and gravity intertwine. But let's not get bogged down in the theoretical weeds. The real lesson here is that the quantum vacuum, far from being a passive bystander, may be the puppet master choreographing the cosmic dance on the grandest stages. Its restless fluctuations could be the engine that propels galaxies apart and shapes the ultimate fate of the universe. And that's just the beginning of the quantum vacuum's resume. Some physicists suspect that its seething activity could explain why certain particles, like the electron, have the masses they do. The idea, roughly, is that particles trudging through the vacuum are hindered by their interactions with its fluctuating fields, like a celebrity wading through a sea of paparazzi. The Higgs field, that media darling of particle physics, is just a special case of this. Its non-zero value in the vacuum is what gives elementary particles their heft. But why stop there? The quantum vacuum's tendrils reach into some of the most esoteric realms of physics. Take supersymmetry. The idea that every boson force particle has a fermion matter particle partner, and vice versa. If it's true, the quantum vacuum could be a perfectly balanced dance between these superpartners, canceling out some of those gargantuan energy contributions I mentioned earlier. Or consider string theory, that ambitious attempt to unify nature's forces into a single quantum framework. In string theory, what we perceive as particles are actually tiny vibrating loops of energy, like the notes of a cosmic symphony. And what's the stage on which these strings play out their vibrational drama? You guessed it, the quantum vacuum, where the strings' incessant oscillations ripple and reverberate. Are you starting to see the bigger picture? The vacuum, this entity we once dismissed as empty and boring, is actually the star of the show. It's the conductor of the cosmic orchestra, the choreographer of the particle ballet, the stagehand setting the scene for the grand drama of the universe. But here's what really keeps physicists up at night. We don't truly understand any of it. We have snippets of insight, glimpses of a deeper order, but the full story remains elusive. Why is the vacuum energy so small compared to our theoretical expectations? How does the quantum vacuum give rise to the large-scale structure of spacetime? What fixes the values of constants like the speed of light or the strength of gravity? The answers, if they exist, are hidden in the quantum buzz beneath reality's surface. So the next time someone tells you that space is empty, just smile politely and remember what you now know. The quantum vacuum is everywhere and everything. It's the source code of reality, the backstage crew of the cosmic theater, the hidden puppeteer pulling the strings of the universe. And we've only just begun to decipher its secrets. But this rabbit hole goes even deeper. In the next part, we'll see how the quantum vacuum connects to some of the most profound questions in the foundations of quantum mechanics. Questions about the nature of measurement, the reality of the wave function, and the quantum to classical transition. You won't look at empty space the same way again. If your classical worldview is feeling shaky, good. That's the first step towards a quantum leap in understanding. Keep following along, and let's see how deep this vacuum rabbit hole really goes. You won't look at empty space the same way again. If your classical worldview is feeling shaky, good. That's the first step towards a quantum leap in understanding. Because when it comes to the quantum vacuum, things are about to get downright bizarre. Let's start with a seemingly innocent question. What happens when you try to measure the quantum vacuum? Naively, you might think, nothing at all. After all, how do you measure a void? But that's classical thinking, and it's about to lead us astray. Imagine setting up the perfect vacuum, free of any particles or radiation. Now place a detector in that vacuum to measure its energy. And here's where it gets weird. That very act of measurement will cause the vacuum's energy to fluctuate. The particles will suddenly pop into existence as if from nowhere, just to satisfy the constraints of the uncertainty principle. It's like the vacuum is a sleeping dragon, and your measurement just poked it with a stick. The dragon awakens roaring with quantum fluctuations that were previously dormant. The more precise your energy measurement tries to be, the wilder the fluctuations become, is a consequence of Heisenberg's famous uncertainty principle. The more you nail down one quantity, like energy, the more uncertain its conjugate quantity, like time, becomes. But it gets stranger. Those fluctuations aren't just random noise. They have structure, pattern, coherence. In the right circumstances, they can even coalesce into real, observable particles. Physicists have a name for this surreal phenomenon: particle-antiparticle pair production. Here's how it works. The quantum vacuum is like a vast ocean of potential energy. And just like real oceans have waves, the vacuum has ripples, tiny oscillations in its underlying quantum fields. Normally, these oscillations are perfectly balanced. For every crest, there's an equal and opposite trough. The net energy is zero. But when you add energy to the vacuum, like in a high-energy particle collider, those ripples can grow into towering waves. If the wave crests get high enough, they can spontaneously break into particle-antiparticle pairs. An electron and a positron, for example, which then shoot off in opposite directions. It's like the vacuum is a cosmic magician conjuring matter and antimatter out of thin air. But here's the kicker. Those newborn particles don't last long. They're like mayflies, flickering into existence for the briefest of moments before annihilating back into the vacuum. The more energy you pump in, and the more pairs you can create, but they always balance out in the end. It's as if the vacuum abhors an imbalance in its energy books. This constant dance of creation and annihilation is happening all around us, all the time. Even in the emptiest vacuum of space, particle-antiparticle pairs are shimmering in and out of existence like quantum fireflies. The universe is never truly at rest. But if particles can emerge from the vacuum, what does that say about the nature of particles themselves? Are they really fundamental, indivisible entities, or are they just localized ripples in an underlying quantum field? This is where the concept of wave functions comes in. In quantum mechanics, particles don't have definite positions or velocities. Instead, they're described by wave functions, mathematical entities that encode all the probabilities of finding the particle in various states. The wave function is the particle, in a sense. It's the quantum blueprint from which reality is constructed. Now, when you measure a particle's position or momentum, something peculiar happens. The wave function collapses, snapping from a nebulous cloud of probability into a single definite value. It's as if the act of measurement forces the particle to choose a single reality from a menu of quantum possibilities. But what causes this collapse? Why do wave functions behave one way before measurement and another way after? This is one of the deepest mysteries in quantum mechanics, and it's intimately tied to the quantum vacuum. And one provocative idea is that the vacuum itself is responsible for wave function collapse. According to this view, what we call particles are really just stable patterns of excitation in the underlying quantum fields. When we measure a particle, we're not really measuring an independent entity. We're probing a localized quiver in the fabric of the quantum vacuum. And that fabric, as we've seen, is never silent. It's always alive with quantum fluctuations, a ceaseless hum of creation and annihilation. Some physicists suspect that it's the interaction between these vacuum fluctuations and the wave function that causes collapse. The vacuum in this view is like a noisy background that decoheres the wave function, forcing it to choose a single classical reality. If that's true, then the quantum to classical transition, the boundary between the fuzzy quantum realm and the sharp-edged world of our experience, is ultimately mediated by the vacuum. The same vacuum that accelerates cosmic expansion and bestows mass to particles is also the arbiter of quantum measurement. It's the backstage manager that keeps the quantum show running smoothly. But here's the thing. We don't know if any of this is true. The nature of wave function collapse, the quantum to classical transition, the interpretation of quantum mechanics itself. These are all open questions, fiercely debated by physicists and philosophers. What we do know is that the quantum vacuum is central to all of them. And that's really the main lesson I want you to take away from this mind-bending journey. The vacuum isn't just empty space. It's not a passive stage on which the cosmic drama unfolds. It's an active participant, a principal actor, perhaps even the lead role in the grand theater of reality. In the final part of this series, we'll explore perhaps the most breathtaking idea of all, that everything, matter, energy, space, and time could emerge from the quantum vacuum. We'll encounter ideas like the holographic principle, which suggests that the universe is a projection from a lower dimensional reality. And we'll grapple with the ultimate question. Why is there something rather than nothing? So stay tuned, fellow quantum explorer. The best is yet to come. In the meantime, ponder this. The next time you look up at the night sky and marvel at the emptiness of space, remember that the real action is in the void. The quantum vacuum is singing a song of creation or destruction and infinite possibility. And we're just learning to decipher the lyrics. If you're ready for the grand finale, a quantum odyssey that will make your classical notions of reality seem quaint, then join me for the last installment. But fair warning, there's no turning back once you've seen how deep the quantum rabbit hole goes. If you're ready for the grand finale, a quantum odyssey that will make your classical notions of reality seem quaint, then buckle up, because we're about to explore perhaps the most audacious idea in all of physics, that the entire universe, from the subatomic to the cosmic, is a vast hologram projected from the quantum vacuum. Let's start with a seemingly unrelated question. What happens when you throw something into a black hole? According to classical general relativity, it's gone forever. The black hole is a cosmic garbage disposal, shredding and swallowing anything that crosses its event horizon. Information, like the unfortunate astronaut you just tossed in, is irretrievably lost. But there's a problem with this picture. Quantum mechanics has a strict rule. Information can never be lost. It can be scrambled, entangled, hidden in the haze of probability, but never destroyed. So what gives? How can we reconcile the information-devouring black hole with the information-conserving laws of quantum mechanics? Enter the holographic principle. Pioneered by physicists like Gerard Hooft and Leonard Susskind, yes, yours truly, this audacious idea proposes a stunning solution. What if the information swallowed by a black hole isn't lost inside it, but smeared on its surface? What if, as the old saying goes, the universe is like an onion? And as you peel back the layers of reality, you find that that all the information is encoded on a thin membrane at the edge. In other words, what if the 3D universe we inhabit is a hologram, a projection from a 2D reality? I know, it sounds like science fiction, but the math checks out. Theoretical calculations show that the information content of a region of space, all the bits and bytes needed to describe it quantum mechanically, scales with the area enclosing the region, not its volume, just like a hologram. But it gets weirder. This holographic encoding isn't just a black hole curiosity. Some physicists believe it's a general principle of nature, that the entire cosmos, from the Planck scale to the cosmic horizon, is a holographic projection. Imagine for a moment that our universe is a 3D video game. All the complex physics we observe, the colliding galaxies, the swirling electrons, the dancing superstrings, are just the in-game effects, the renders on our cosmic screen. But the true reality, the actual lines of code that generate this grand illusion, lives on a distant 2D boundary, a cosmic CDROM, if you will. And what is this boundary, this ultimate hard drive of reality? You guessed it, the quantum vacuum. In the holographic view, what we perceive as the vacuum's ceaseless fluctuations, its bubbling quantum foam, is really the flickering pixels of the cosmic hologram. The vacuum isn't just the stage on which the universe unfolds, it's the projector screen. But here's the real kicker. If the holographic principle is true, then everything, and I mean everything, emerges from this quantum hologram. Space-time itself, the very fabric of our 3D reality, is a projection from the 2D boundary. The vacuum isn't just the origin of matter and energy, it's the source code of reality itself. In a sense, we're all just holograms, shadows on Plato's cave wall. The true reality is the quantum bits dancing on the cosmic horizon. Now, I know what you're thinking. This all sounds like metaphysical mumbo-jumbo, a far cry from the hard science of lab coats and accelerators. But the holographic principle has teeth. It's not just a philosophical flight of fancy. It's a mathematically robust framework that's shedding new light on some of the deepest problems in physics. Take quantum gravity, for instance. For decades, physicists have struggled to unite the smooth continuum of general relativity with the choppy quantum realm. How do you build a theory that describes gravity as a fundamentally quantum phenomenon? The holographic principle offers a tantalizing clue. In the holographic view, gravity isn't a fundamental force at all. It's an emergent phenomenon, a side effect of the quantum bits jostling on the boundary. Just as the illusion of depth emerges from the flat pixels on a screen, the warping of space-time emerges from the entangled qubits of the cosmic hologram. Gravity, in this sense, is the ultimate special effect. And that's just the tip of the iceberg. The holographic principle is also intimately tied to string theory, the leading candidate for a theory of everything. In string theory, the fundamental building blocks of nature aren't point-like particles, but tiny, vibrating loops of energy. And guess where these strings do their cosmic dance? That's right, on the 2D boundary of the holographic universe. In fact, some string theorists believe that the entire 10-dimensional fabric of string theory can be encoded on a lower dimensional boundary, that the quantum fluctuations of the vacuum are really the symphony of strings playing out on the cosmic horizon. But perhaps the most profound implication of the holographic principle is what it says about the nature of reality itself. If the universe is a hologram, then everything we experience, the solid ground beneath our feet, the stars wheeling overhead, even our own bodies and minds, is, in a sense, an illusion, a projection from a deeper, truer reality. It's a dizzying thought, one that threatens to upend our most cherished notions of what's real and what's not. But it's also a testament to the power of science to peel back the layers of reality, to reveal the hidden machinery whirring beneath the surface. And at the heart of that machinery, the engine that drives the cosmic hologram is the quantum vacuum. That seething, restless entity that we once dismissed as mere nothingness, but now recognize as the source code of everything that is, was, or ever will be. So the next time someone tells you that empty space is boring, that the vacuum is a void, just smile and remember, the quantum vacuum isn't just a part of our universe. In a very real sense, it is our universe. And we're just the holograms projected on its shimmering surface. If this journey through the quantum looking glass has left you reeling, good. That's the first step towards breaking the true nature of reality. The classical world of our everyday experience is but a flickering shadow of the quantum realm beneath. And the more we probe that realm, the more we realize that everything we thought was solid and certain is actually built on a foundation of pure potentiality. That's the real magic of the quantum vacuum. It's not just the infinity between the stars or the emptiness within the atom. It's the wellspring of reality itself, the source code from which everything else emerges. And we're just beginning to hack its secrets. So stay curious, my fellow quantum explorers. Keep probing the void. Keep questioning your classical assumptions. Because if there's one thing the quantum vacuum has taught us, it's that the deepest truths are often hidden in the most unlikely places. And who knows, maybe, just maybe, if we stare into the abyss of the quantum vacuum long enough, it will start to stare back. Thank you for joining me on this mind-bending odyssey through the quantum void. If you're hungry for more reality-warping insights, be sure to like, share, and subscribe. Because in a holographic universe, every new perspective is a window onto the infinite. Until next time, keep questioning everything, even nothing.